He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
Well, this is a bummer, isn't it?
It is. It's not the best. It's not the best.
Lost in space is the colloquial phrase for what's happened. Apparently it went off course about 10 days ago.
Somewhere out there, somewhere in the lonely annals of space, there is a satellite that beeps no more.
Kia ora, nau mai haere mai ki te ao hurihanga. Ko Ellen Rikers tēnei. Hello and welcome to Our Changing World. Back in early July, New Zealand got some bad news. A satellite built to detect the potent greenhouse gas methane had gone dark. The satellite, named MethaneSAT, was a project of US-based non-profit, the Environmental Defence Fund, but New Zealand had a stake in it too. The government had got on board to the tune of $30 million, and this was the country's first major government-backed space mission. With the satellite first launched into space in March 2024, the University of Auckland were poised to take over mission control. But then contact was lost and the satellite deemed unable to be recovered. MethaneSAT was built to spot big leaks of methane from oil and gas fields. Plugging these is a potential easy win for reducing global emissions of a greenhouse gas that is 80 times more potent than carbon dioxide over a 20-year period. But an add-on mission, led by New Zealand scientists, aimed to see if it would be possible to pick up smaller, more diffuse methane emissions, like those from belching sheep and cattle spread out over large areas of pasture. In New Zealand, methane makes up almost half of our greenhouse gas emissions, with the majority of this coming from agriculture. So this unique emissions profile makes New Zealand a good place to test the satellite's cow burp detection capability. Why use a satellite, though, in the first place? Well, getting MethaneSAT to do this job could theoretically help find agricultural methane hotspots around the world. It could potentially detect and quantify methane that's harder to study using ground-based methods. Or maybe we could even use it to check whether efforts to reduce methane are actually working. But was MethaneSAT even technically capable of this, or would it be beyond the satellite's limits of detection? And what did New Zealand get out of the $30 million investment, given the satellite was only in space for a little over 1 year? Let me take you back to earlier this year. MethaneSAT is still orbiting and communicating. It's a hot day in March, and researchers from Earth Sciences New Zealand, then known as NIWA, are on the ground in Canterbury. I catch up with them at an airfield near Christchurch. Just before MethaneSAT crosses high above us, a light plane is preparing to take off with pilot Ivor Yockney at the helm.
Flying transects today for some research air sampling.
When you say flying research transects, I mean, what will that look like if I'm standing down here on the ground and see your little plane?
Yeah, well, probably best what you see is on flight radar if you track it on those online apps. But yeah, just basically straight lines at certain heights.
And what do you expect it to be like flying today? It's a pretty beautiful day down on the ground.
Yeah, it's pretty good. There's a slight nor'west up top, and it's going to go nor'west later on today. But I think the planes will be really good, probably better than yesterday, and doesn't look like as much cloud as yesterday.
On board will be 2 research students and a device for measuring methane. The idea is that this plane will fly under the path of the satellite, so that both are collecting data from the same area. The satellite, orbiting Earth 15 times every day, will spit back its measurement from a distance. Meanwhile, the plane will produce measurements from within the atmosphere at different heights. Here's Harrison O'Sullivan-Moffat, a PhD candidate at Earth Sciences New Zealand and Victoria University of Wellington.
For this purpose here today, the satellite will be measuring methane from space, and we are trying to make sure that the satellite is measuring the same as the actual air. Remote sensing is the same as in situ.
Right, so the device is actually physically taking some air from outside the plane and measuring how much methane is in it.
Yeah, exactly.
Harrison's PhD project is to compare these 2 measurements. Is the satellite getting it right? And can it pick up on changes as the day unfolds and cows burp and the wind blows? He's doing the sense check for both Canterbury and Waikato.
They're two of the most agriculturally productive regions in the country, and Canterbury is very flat, so hopefully the winds are a bit more predictable than other places. Also, the satellite target image is a square, and Canterbury is a square region geographically.
That's convenient.
Yeah.
While Harrison gets ready to take off, I'm staying earthbound, and that's because in addition to the data from the satellite and the plane, there are 4 ground-based instruments dotted across the Canterbury Plains that will also be collecting methane data. So I'm heading off with atmospheric scientist Dr. Alex Geddes.
Based down in central Otago, but up here in Canterbury doing it on a beautiful day doing ground-based validation of MethaneSAT.
Great, and so we're about to head off from the airfield. Whereabouts are we heading to?
We're off to Pegasus Beach, and we're going to set up an instrument there, an EM27, which is a ground-based spectrometer that looks up at the sun. Hopefully it'll stay clear, and that's going to be used to characterise the inflow from the ocean into the kind of Christchurch Canterbury region.
Fantastic. Cool. All right, well, we'll jump in the car and head over there now.
Let's get going.
We make the drive out to the beach and find a patch of grass next to the car park to set up the instrument.
So this is the instrument itself. This is called an EM27.
It almost looks like slightly bigger than a home printer.
Yeah, almost like same as a home printer or like a large microwave, maybe that kind of size.
Yeah, like microwave size. Good description.
But quite heavy. I've been going to the gym, so it's all good. So essentially what they're trying to do now is, this part here is the solar tracker, and it sends sunlight into the spectrometer, which is in the big kind of part of the instrument essentially. And so now we've got to align it to north, turn it all on, and hope that we can then find the sun in the sky with the tracker. And then once that's going, everything's sweet, and we should be measuring away.
There are 4 of these EM27 spectrometers across the Canterbury Plains. Another one at Rakaia Huts, which fellow scientist Dave Pollard is operating, and 2 automated sites at Clearview and Ngaitahu Research Centre.
If you have more than one, you can triangulate, you can surround an area, you can calculate inflows, outflows of the gases moving through the areas. Plug in the power and communications cables. So we need power first, so we've got basically a huge hefty battery here. Okay. So that you'd find in a caravan essentially. And we're going to use this to run the instrument for the next few hours. In some of the permanent sites we have power and Ethernet hookups, which is really great, but in remote sites like this, either run out from the car or better solution, just bring a battery, you don't want the car going flat.
Both the EM27 and MethaneSAT detect methane in the atmosphere by looking at sunlight. Different gases interact with the sunlight in different ways, which leave characteristic fingerprints in the sunlight spectrum. So, the EM27 is set up to track the sun as it travels through the sky.
So that sound is the tracker moving to where it's the tracker motor driving the system, and it's moving to where it thinks the sun should be. Awesome source, I think we're good to go. So now what it's doing is it will always be following the sun now, automatically, as the sun moves through the sky. And then every couple of minutes we'll get a spectrum on the screen, every few seconds rather, we'll get a spectrum on the screen, which is monitoring how that light's changing. So as we'll see in a couple of seconds when one comes up, but as light passes through the atmosphere, it interacts with the different gases in the atmosphere, and each gas has its own signature, its own fingerprint essentially. What that looks like is an absorption line, so different gases absorb in different wavelengths or different kind of colours. And by measuring those kind of absorption bands, we call them absorption lines, and how they change, you can then work out how much of a gas there is. So by looking at how strong and deep and wide those lines are, that gives you a read of how much of a particular gas is in the atmosphere. And you do that, for methane in this case, but this spectrometer can do it for CO2, it can do it for a whole range of other gases, and it's a very, very nice way of measuring it. And the satellite works in the same way. The only difference there is the satellite's looking down at the surface of the Earth, with sunlight being reflected off the surface back into space. The reason we're doing these kind of measurements is because they're philosophically identical to what you can do from the satellite. So we're using similar wavelength ranges, similar techniques. It's at the same time using the same source of light, which is in this case the sun. So it is the way to validate these kind of things, to do it from the ground. So the MethaneSAT will take a 200 by 200 kilometre approximately snapshot of the surface of New Zealand. And by having multiple EM27s across that region, it allows you to diagnose how well they align with what MethaneSAT is seeing, but also if there's any spatial variations that aren't physical, they're more of a kind of satellite product. Maybe there's some kind of errors in the way the satellite collects that information.
So the science team are checking that both the EM27 and MethaneSAT are seeing the same methane levels. Having 4 EM27s spaced out across the measurement area also allows them to pick up methane gradients across the landscape and figure out where the methane might be coming from. Plus, the plane is making direct measurements of methane in the air, mapping it across the area and at different heights.
And likewise with the aircraft, you can look at how that concentration changes across these transects. So flying upwind versus downwind, you should hopefully see that downwind there's more methane than there was upwind because there's been emissions in between. And then by looking at that difference, you can then calculate how much methane has come from the area that you've overflown, essentially.
And so what about the satellite? What is it doing now? Is it going to pass over us?
Yep, any minute now, essentially. It should be taking a look.
Okay.
And that'll be doing the same thing as the EM27s. It'll be measuring an average concentration over the atmosphere, but they'll be measuring it at very, very high spatial resolution. So the EM27s are just in one place, but the satellite can see over a 200 by 200 kilometre area, but with pixels, essentially little subsets of that down to a couple hundred metres, essentially.
In other words, MethaneSAT is capturing a bird's eye view collage or a patchwork quilt of data, where each patch represents an area of land. The EM27s are getting point readings on the ground, and the plane is taking readings in between. You need all three to figure out whether you can pinpoint what's emitting methane on the ground using MethaneSAT. Imagine a plume of smoke swirling up into the air and being buffeted by the wind, mixing in turbulent air currents as it propagates upwards and diffuses. The higher up you go, the harder it is to track the source of the plume, unless you know how it has behaved closer to the ground, and then you can use that knowledge to build a model. Giant plumes off, say, a leaking gas field, they're easy. Smaller plumes from farms, they're much harder. MethaneSAT is looking for things like landfills or things coming off oil and gas fields, but here in New Zealand we're really interested in agriculture.
Yeah, totally.
So this project is kind of seeing whether that's even possible to see that level of resolution, is that right?
Yeah, absolutely. And New Zealand is the place to test it. I mean, the farming community here, the inventory teams here are some of the best in the world, so we know what our emissions are. We have a very kind of clean environment. There's no big pollution. If there is methane in New Zealand, it's pretty much guaranteed to be from agriculture. There's, I just say, not much oil and gas, nothing like that. So if you're going to attempt to do this, the place that you try to do it first is definitely New Zealand.
Do you think it will be possible?
Yeah, I think so. I mean, I think you've just got to have put caveats on that. I don't think we'll get down to the point where we could say this farm is doing this, emitting this amount. I think that's still a way away. The scale of the outputs, I think, would be hopeful to get down to something like the tens of kilometres scale. So estimates over a 20 by 20 kilometre area would be really good. But of course, it really depends on the amount of animals in any one place. The density of animals is really what drives it. You need enough signal, essentially. So the more dense the animals are, the higher the likelihood that you can reduce that scale down and go to like a 10 by 10, for instance. That would also be possible. There's different to say in the US and Northern Europe, where you might have a lot more huge kind of scale feedlots. You'd be able to capture them because there'd be on the larger ones, would be maybe over 100,000 animals in one particular place. So that should stand up quite nicely. But otherwise, yeah, you might need to integrate or add up over a larger area to be able to say anything with confidence about the emissions.
So that would be a challenge in the New Zealand context. We typically have more herds roaming the pastures.
Totally. And that doesn't mean we can't do it, but it'll be, we have to have restraint and think about, what scales are appropriate and what point are we confident, essentially? You don't want to, we could estimate at 1.5 kilometers, but it won't be worth anything. It only becomes valuable and statistically significant when you get to that kind of 10 or 20 kilometer area. So it's, what we'll do over the next few months once we've got some data is look at that data that we have and see where we land and what we can deliver.
Ultimately, the idea would be to advance the science and satellite capabilities enough that you could provide farm-level estimates, and to track changes in methane concentrations over time, because that could provide proof that things like feed additives or breeding for lower methane livestock are actually working to reduce methane in the real world. But that's future stuff, and it's not something MethaneSAT could have feasibly revealed. That's according to New Zealand experts who provided feedback to the New Zealand Space Agency. Back in the field, it's time to wrap up. And if you're wondering, how big is MethaneSAT?
So about the size of a mini fridge.
A mini fridge. So
but weighing 350 kilograms.
A very dense mini fridge. Lots of drinks in that one.
Yeah.
So that's flown overhead now.
Yep, so that hopefully has gone over about 20 minutes ago.
Okay.
And hopefully captured a really nice scene of Canterbury. It's a little bit of it's a pretty good day. It's a little bit of cirrus cloud knocking around, but hopefully not too much, and hopefully we can still get a nice clean scene and hopefully be one of the better days for sure.
A couple of months after recording this audio, I was sitting down to edit when a breaking news banner popped up on the RNZ website. RNZ's climate correspondent, Eloise Gibson, had been asking about issues with MethaneSAT since September 2024. Control of the satellite was supposed to have been transferred to the University of Auckland. Instead, control had been passed back to the satellite's developers in Colorado. The mission's chief scientist had admitted that there were issues with solar activity and the satellite's thruster. But now, disaster.
Someone called me up and said, we've got bad news. And I'm going to be honest, it broke my heart a little bit.
That's Dr. Sarah Mikaloff-Fletcher. She's the science leader for MethaneSAT Science Project. The bad news, contact with MethaneSAT had been lost.
Losing the satellite, that was hard for everybody involved in this mission. And it was real sad. It was planned as a 3 to 5 year mission. And, it was really in the sky for a year and a bit. So it was really sad for everybody involved. But in the time that MethaneSAT flew, we did get a lot of data.
Remember that MethaneSAT's main goal was to identify oil and gas leaks, because plugging these is seen as an easy climate win. And it did collect evidence of higher than estimated methane spillages. In particular, it picked up a whole heap of smaller, dispersed sources of methane that hadn't previously been picked up by other satellites. And when added up, these were significant. Plus, early observations suggested that emissions from oil and gas production areas in North America and Central Asia are significantly higher than what's currently reported.
Those emissions tend to be really big emissions over small areas. So they make a big plume that's pretty easy to see from space compared to other things. Whereas agricultural emissions, especially agriculture the way we do it in New Zealand, where it's really, cows in the field, grazed agriculture, that's a much more diffuse and dispersed emission. It's harder to measure and quantify from space. And we're going to be the first people who can do those emissions from remote sensing data. And even though I'm very sad about losing the satellite, that opportunity is still incredibly exciting.
Why use a satellite? Could you not just do this with planes?
Yeah, you could. There are a lot of different ways that you can know what the methane emissions are for agriculture. But the idea of doing it with a satellite is that you could have one instrument that you could use to map methane emissions at a lot of places around the world so that you could better understand those emissions in places where it would be really expensive or hard to do a ground campaign, and over a much larger spatial scale. New Zealand's really the ideal place to test that capability, partly because we have a lot, agriculture is very important to us, right? We feed a lot of people around the world. So we have really high agricultural emissions, but we also have a really strong track record in atmospheric measurements, in being able to understand those agricultural emissions from the ground-based approach, and in the type of atmospheric modeling that you use to backtrack from what you see from the satellite, which is methane concentration, to what you need to know for policy, which is actually those emissions. So it's really kind of the perfect little test bed to prove that capability.
During the year and a bit MethaneSAT was in space, it looked at 97 different agricultural targets around the world, including 13 in New Zealand.
I think the good news is that all of the data we have, I mean, it's really beautiful. You know, the precision looks amazing, and there's really strong alignment with what we saw from the ground-based field campaign, what we expect from the modeling we did pre-launch, and what we saw from the satellite data. So, all of that work is still going to provide new information about agricultural emissions from those targets.
And what about the big question? What scale of agricultural methane could the satellite actually pick up? When I spoke to Alex, and he said, we're kind of trying to figure out the minimum threshold for detecting cow burps. And so you're not going to, I'm guessing you don't detect a single cow burping. So what's the kind of scale that you were able to achieve?
Well, that's a more complicated question than you think, and we're still also working on it. So we have the data, but we're still processing the data and trying to understand how well it works and applying some specific models that we've developed here in New Zealand to being able to do those emissions from that data. So I don't know exactly what that minimum number is just yet, but you could probably ask me again in 6 months and I would know more. But it also depends on the area over which you want to know that answer. So MethaneSAT scans with a native resolution of it maps with a native resolution of 100 by 400 meters. But if you have a more diffuse emission with fewer cows, you might be able to get a better answer if you only need to know it over a larger area than that native resolution. I mean, we definitely see facility scale for places where you have more intensive agriculture. So we can definitely see facility scale for larger dairies that you might see in places like the United States. But for diffuse agriculture, I can't give you an answer yet.
So yes, MethaneSAT could spot the methane from individual farm facilities where the animals are densely packed into a small area, like feedlots. Plus, the data revealed unexpected variability in emissions from these big feedlots in the US, where there's lots of, cow poo. But for New Zealand data, you might remember Harrison, who flew on the plane to collect methane measurements. And his whole PhD was built around comparing data from MethaneSAT to the plane and to ground-based measurements. So has the loss of the satellite affected his project?
It hasn't. The great thing about the Harrison's PhD and also our other PhD student, Kirsten, is that by the time we lost contact with the satellite, all of the data we needed for their PhDs was in the bag. So he'd completed all the field campaigns that were planned. We'd had really good data from overpasses during those field campaigns. And although there won't be future MethaneSAT data, a lot of his question is really around understanding what you need to be able to do this problem well from remote sensing. And MethaneSAT is it's a very special satellite. There's nothing quite like it. But it's not the only satellite that does methane in the sky. And there are a lot of missions upcoming as well that seek to quantify methane emissions from space. And so that larger question of what does it take to do this problem well? What are the limits of this problem? And what kind of ground-based measurements do you need to verify or add to these satellite measurements? Those questions are all still really relevant to ongoing and upcoming work. So I anticipate that he's going to have a great PhD and that his papers are going to be valuable to the community.
Sarah is hopeful that this is not the end of New Zealand's involvement in satellite-based detection of methane.
Well, we're analyzing the MethaneSAT data now and doing the modeling on that. And we're also going to pivot a little bit and use the modeling capability that we've developed for this project to work with another satellite that's a European instrument. It's flying on board Sentinel-5 precursor. It's called TRPOMI. And TRPOMI doesn't have quite the precision or the spatial resolution of MethaneSAT, but it's the best thing in the sky currently. And it's been running for quite some time, and it has a daily return time. So it measures on a very high time frequency. So we hope we can get some more information about trends and variability if we can get the methods to work with TRPOMI despite its lower precision.
As for mini fridge-sized MethaneSAT, lost somewhere in orbit, well, its future isn't too bright.
The two things I know are that we lost contact with it, and we also lost attitude control. So, it probably exists there, and eventually it will decay and burn up in the atmosphere.
Thank you to Dr. Alex Geddes, Harrison O'Sullivan Moffat, Mackenzie Purtle Wright, and Dr. Sarah Mikaloff-Fletcher from Earth Sciences New Zealand. Thank you also to Ivor Yockney from Canterbury Aviation. This episode was produced by me, Ellen Rikers, with help from Our Changing World presenter and producer Claire Concannon. Sound engineering was by Mark Chesterman. Tēnā koe I whakorongo mai. Thanks so much for listening. Have a great week. Kia pai te wiki.